Okay, so what I'll do today is explain the chemistry with respect to the lab report. For this lab, you will not be on LabFlow, you will be in Canvas. Both your pre-lab and your lab report are in Canvas. So we'll talk about the experiment, we'll look at the procedure, and then, we'll also look at the pre-lab as well as the post-lab. And then you can take the afternoon off, work on everything. I'm going to come back online at 2:30. So 2:30 to 3:30. If you have any questions with Williamson ether synthesis or acylation of ferrocene or anything with the lecture, come back, join me at 2:30 to 3:30, and then we'll talk about that. So let's start with acylation of ferrocene. So as we know clearly from the title itself, this is a Friedel-Crafts acylation. So we are looking at a Friedel-Crafts reaction. So typically the reaction is taking benzene, just to review very quickly, taking an acid chloride. So this is our acid chloride. Our classic catalyst is aluminum chloride. So we are going to substitute a hydrogen. So a side product is HCl, plus you'll get the substituted product, which is a ketone. So what you're forming here is an aromatic ketone. If your R is hydrogen, then you will form an aromatic aldehyde. The structure will be an aldehyde. So your classic catalyst here is aluminum chloride. We are looking at a greener modification of this reaction. And let me explain what today's reaction is, and then we'll compare and contrast to see what's green about this reaction. First and foremost, we are not using benzene, we are using ferrocene, which is relatively a lot safer and easier to handle. This is a yellow solid, whereas benzene is a carcinogenic liquid. We are not going to use acid chloride. We are going to use a modification of this, and this is an acid anhydride. We can use an acid chloride, but an acid chloride is more corrosive. So when you open a bottle of the acid chloride, there's a lot of fumes, and this breathing in those vapors is definitely unhealthy. And acid anhydride is not volatile, so you're not going to get fumes as you open the bottle. So it's a lot easier to handle. You can see it has a much higher boiling point, and therefore it's easier to handle. But it is a liquid, so you'll be measuring it using a measuring cylinder. Our catalyst is not going to be aluminum chloride. Aluminum chloride is a Lewis acid. Aluminum is less than octet. It has only 6 electrons, so it's quite hungry for electrons. It's a very strong electrophile. It's constantly looking for a pair of electrons. You open a bottle of aluminum chloride, you get a lot of dense white fumes because it immediately starts reacting with the moisture in the atmosphere, trying to grab a pair of electrons from the oxygen in water. Instead, what we're going to use, an alternative, is your phosphoric acid. This is our replacement for the corrosive aluminum chloride. Typically, these reactions involve a solvent. The solvent is usually, nonpolar solvent is used, or a mix of nonpolar and polar. But here, our phosphoric acid also functions as a solvent. So it is both a catalyst as well as a solvent. It can also function as a solvent. One other thing that can function as a solvent for us is acidic anhydride. So our limiting reactant here is ferrocene. So once the ferrocene is used up, the reaction stops. The excess acidic anhydride, which functions as a solvent, can be easily destroyed. Our major product expected is the acetylferrocene. You can see the acetyl group, the ketone group added to ferrocene. This is our minor product that may form. Now, first and foremost, we know this is a reaction of the benzene ring, reaction of the aromatic compound. So we want to know whether ferrocene is aromatic. So there's a lot of chemistry involved here. So let's take a look. In ferrocene, you have 2 cyclopentadienyl rings. So we have this, a lone pair, negative charge. We have another one, lone pair, negative charge. Your ion is 2+. So your ion combines with 2 cyclopentadienyl anions. So we got 2, 2, 2. Your very popular 6-pi electron system. So both rings are aromatic. So ion combines with these two rings, and therefore the entire molecule is aromatic. This is ion 2 plus. Okay. Now, how do we draw this particular molecule? So I want to take first one cyclopentadienyl ring, and you can see that this negative charge can move around. So you can draw resonance structures. So I'm going to quickly draw these resonance structures. I'm not going to spend too much time explaining this. You know how to do this. So a quick rotation of those pi bonds will generate a total of 5 resonance structures for me. So there is my last one. This is my 5th resonance structure. And take a look at each of the resonance structures, every carbon atom. So if I call this 1, 2, 3, 4, and 5, you can see the negative charge on the first carbon, on the third carbon, 5th carbon, 2nd carbon, 4th carbon. So every carbon atom shares this negative charge. So each carbon atom has 1/5 of the negative charge. So the negative charge is delocalized inside the cyclopentadienyl anion, both the top ring as well as the bottom ring. So when you draw a structure for this, what you do is you simply draw a circle, which indicates that those 6 pi electrons are delocalized inside the ring, just like benzene, and then draw a line right in the middle here that connects your ion. So this molecule is called ferrocene. It is like a Big Mac sandwich. So this is also called a sandwich complex. It's an organometallic compound that is aromatic. So it's going to react like benzene, which means it's going to undergo substitution reaction just like benzene. So let's see how this happens. So what I'm going to do now is I'm going to draw one cyclopentadienyl ring here with a circle, okay? And then what I'm going to do is, just to make our mechanism clear, I can move, I can draw an arrow from the circle, but I can certainly draw it from the negative charge. So I'm drawing one of the 5 resonance structures for the top ring only. Then I have my acidic anhydride. So this is my acidic anhydride. I'm opening up the structure and writing a condensed structure here. You have phosphoric acid. So what the phosphoric acid is going to do is protonate one of these oxygens. So it's going to have only one lone pair positive charge. So what it's going to do is pull electrons towards it. So it's going to make this carbon right here more fond of electrons. It's going to make it more nucleophilic, and so the reaction will take place quickly. So the negative charge is now going to attack this carbon. This is going to go like this. So this is your 1, 2 arrows. So what I'm going to do is connect my C here, OH here, CH3 here, OC double bond O, CH3. And while I'm doing that, I'm going to make a little modification here with this hydroxyl. I'm going to pull that oxygen hydrogen bond. And keep in mind, on every ring here, you have a hydrogen. So we have that. All right, so we have a hydrogen here. We have a positive charge on that ring right there. So when you have acids, keep in mind you have water, okay? That's something you're definitely going to have. So the water is going to grab this proton. This is going to drop like this. This is going to go like this. So I have arrows 1, 2, and 3, which will lead to the formation of the product. It's not complex, except that I think it's a little bit different. So I have my hydrogen, ion over there. So you're going to use water or you can use this acetate. That's your choice. So it's going to grab the proton, drop that inside the ring. Okay, so you're going to get back your aromaticity, very similar to that of benzene. So what you do now in the last structure is you simply put that ring back on and you attach the ion. So you're showing a substitution here of the acetyl group. So bring the whole thing back on the screen to explain this again. What I'm doing is intentionally using one of those 5 structures, and that's going to attack this. So this is our nucleophile. Because you're asked this question in the pre-lab. This is your nucleophile. Your acetic anhydride receives the electrons, so that's our electrophile. Phosphoric acid is a catalyst. It makes this particular carbon here that I'm darkening out more nucleophilic, which means it's gonna make it have the nucleophile attack it more. It's gonna make it grab those electrons more. So it's gonna make it more electrophilic. That's what I should say. Then what I'm doing is this is your leaving group. So this leaves. And then finally, I'm restoring the aromaticity here. Okay. So this is the reaction mechanism. It's also given in your lab report if you want to look at that. Now, the bottom ring can also react. If it does react, that's when you get this diacetylferrocene. But this is going to be a minor amount because we are not going to add that much excess of acetic anhydride. We are not going to add a large excess, but keep in mind, this is our excess reactant and this is our limiting reactant. So it is possible to get a minor amount of this diacetyl product. Okay. Ortho, meta, para cannot be used because it's not a benzene ring. So we don't say that the groups are ortho, meta, and para. This is ferrocene. This is not benzene. So that terminology will not be applicable here. Okay, so keep that in mind. So any questions on the mechanism or the reaction? Now, it's a nice visual reaction. The reason I say that is the ferrocene is a yellow solid, but this is a deep orange red solid. So you see an immediate transformation of the color. The reaction takes about 5 minutes. That's all it does. And in 5 minutes, the reaction is done, but usually we let it go for about 15 minutes to get a pretty high yield. So let's see the setup. The setup is quite simple. We're going to do the reaction at 100 degrees. So the most we're going to go with this temperature is 100 degrees Celsius with using a water bath. The round bottom flask will contain ferrocene, acetic anhydride, and your catalyst, which is concentrated phosphoric acid. You'll also add a stir bar. You'll stir the reaction, okay? On the top, you have a water condenser straight up. So what it's going to do is boil the contents of the reaction, and it's going to boil it at the temperature of the solvent, and this is known as reflux. Reflux means heating the solution. You're asked this question as well in your pre-lab, heating the solution to the boiling point of the solvent. So in this case, the boiling point of the water bath, okay? So the highest temperature you would get to it is 100 degrees. It can go more than 100. And if any of them, volatilize, the condenser will bring it down. We don't want any water inside this reaction mixture. So we're going to use a drying tube, and its drying tube is packed with a drying agent. The drying agent used is calcium chloride. The reason we don't want any water inside is because acetic anhydride will react with water and break down, and you don't want it to break down. So if you treat it with water, let's say a little bit of moisture gets in, what will happen is you'll form 2 molecules of acetic acid. Acetic acid is a side product. It is not going to react with ferrocene. This is your reactive component. With ferrocene, this is not going to react with ferrocene. So you don't want your acetic anhydride to break down to acetic acid. Okay, so this is acetic anhydride, which will react with the moisture in the atmosphere to form acetic acid. You don't want this reaction to take place. So any moisture that comes in will be absorbed by calcium chloride, prevents moisture to getting into the system. As I said, the reaction only takes about 5 minutes, but we usually let it go for 15 minutes or so to make sure that we get a pretty reasonably good yield. And that is it with this reaction. It's a fairly straightforward reaction. Now, the greenness of this reaction is because you're replacing aluminum chloride with phosphoric acid. You're also replacing acetyl chloride, acid chloride, with acid anhydride, which is easier to handle. Okay. Instead of using benzene or other kinds of organic liquids, you're actually using a solid that is odorless, that is ferrocene, that's odorless, that's non-volatile. So that's really easy to measure. So, and the reaction takes place very fast. And honestly, to set this up will only take about 15 minutes because you get a round bottom flask, you just attach this condenser, attach the drying tube, and then you should have a stand here, right? And then you have a hot plate and you have a water bath and you're ready to go. Reaction is pretty fast, okay? So that is a little bit about what the reaction in a sense is. What I want to do next, if you have any questions, feel free to stop me. But what I want to do next is go into Canvas and look at some of these questions. So I want to start with the pre-lab assignment. So I'm going to open that up. So let's start with looking at some of these questions. I'll just give you some hints, but I think this lab is going to go pretty easily for you because you already completed aromatic compounds. Classify the general type of reaction and then the specific type of reaction. So what is the general type? What is the reaction we are studying here? And what is a specific type? I'll take one or the other. Which one? Or both? What's the specific name of this reaction? You guys know this, right? Remember? What is this? Friedel-Crafts? Which one? Alkylation or which one? The title of the reaction says it all, right? Acylation reaction. Now I've given you the specific. Tell me what's the general type. What's the general type of this reaction? So this is going to be electrophilic aromatic substitution. Hopefully you haven't forgotten all of that, okay? So general type of reaction is electrophilic aromatic substitution. Specific type is Friedel-Crafts acylation reaction. Why is ferrocene aromatic? So I explained this in the pre-lab. I've recorded it, but you need to maybe upload an image here, okay? So what you want to say here is both I'm going to write CP, okay? Both cyclopentadienyl rings, you want to say something like have 6 pi electrons, planar and cyclic. Therefore, they are aromatic. Therefore, ferrocene is aromatic, okay? So you may want to draw a little picture here showing what I showed you in the pre-lab, you know, how you have 6 pi electrons. It's not too much of a picture, just something really small. Like you can see here, you know, how I'm showing you, you know, how you have those 6 pi electrons that makes both the rings aromatic, and therefore ferrocene is aromatic, okay? So that's the idea here. So a picture would really enhance this. Please let me know if you need any further explanations. Your electrophile is, as I mentioned in the pre-lab, it's acetic anhydride. Your nucleophile is ferrocene. Nucleophile is the one that's providing the electrons. Acetic anhydride grabs the electrons. So if you want to achieve the same results, what can you use in place of acetic anhydride? So in place of acetic anhydride, you can use acid chloride, which is RCOCl. You probably can open that up, right? That is a very good option that you can use to achieve the same result. So what you also want to do here is probably upload a little image explaining this a little bit more. So do something like this. You could say that, you could take the same ferrocene, except that it'll be somewhat corrosive. Yeah, but you do have an alternate. Instead of using acetic anhydride, you can use acid chloride, and then you can use phosphoric acid. You can keep that part of the greenness intact, and then you will get the acetylferrocene. Your side product, of course, you're replacing a hydrogen that will combine with HCl, become, side product. And sometimes, a lot of times, what is used is pyridine. Instead of actually using a catalyst, pyridine is used, and pyridine can combine with HCl and remove it. So this kind of equation might just strengthen the answer a little bit more. So you can explain why aluminum chloride is not used as a catalyst. So please read the lab. I explained this in detail in the lab procedure. Aluminum chloride is corrosive, and the reason it's corrosive is it's less than an octet. It's a very strong Lewis acid, not just a Lewis acid. It's a very strong Lewis acid. It's very electrophilic in nature. It's very corrosive. And apart from that, you also get side products from this aluminum compound, which are like very corrosive aluminum hydroxide products. And then you have to deal with the cleanup of those side products as well. All of this is explained very clearly in the lab procedure, so you could take a lot of information from there. Now let's talk about the next question. I'll move to my other screen here. Now, once you get this acetylferrocene, that's the end of the reaction, but after that, you have something called workup, all right? So what you have in that reaction mixture is this product, but life is never that cozy. You just don't get the product only. You get some excess reactant, right? So you also have this. Right? That's your acetic anhydride. You also have this. This is your excess reactant. And then what's also contaminating that reaction vessel is phosphoric acid, which is a catalyst, and it is regenerated. So you don't have just your desired product. And then unfortunately, you might have a really small amount of your side product. So your question is, why do you use a hot solvent for recrystallization? So the hot solvent that we use is hexanes. Hexanes is a non-polar solvent. Phosphoric acid is polar, acetic anhydride is polar. This diacetyl is definitely more polar. This is relatively less polar. I'm not going to call it non-polar. You won't like it because there's a carbonyl group, but it is the relatively less polar one. So when you use hexanes, which is non-polar, the relatively less polar desired product will dissolve. And when you use hot hexanes, solubility increases with temperature. So you ensure that most or all of your desired product dissolves in hot hexanes and helps you separating it from the diacetylferrocene, which is an undesirable side product, the excess reactant, which is acetic anhydride, and the catalyst, which is phosphoric acid. So that's why I bolded out two things. You want to explain why it should be hot, higher the temperature, greater the solubility. Hexanes, you want to use a non-polar solvent so that you can dissolve your desired product, which is relatively less polar than everything else that contaminates it. Okay. So that is your pre-lab. For this time, you're just going to turn in the pre-lab along with your lab report. So let me just get into your lab report now. You don't get into lab flow at all for this. You just stay in Canvas. So we'll begin this. Any questions? Feel free to ask me. But I'm thinking it's all coming back to you, hopefully. Write a mechanism for the lab. So check the pre-lab recording here. Okay, I have the mechanism written in detail. You can take that. Why is acetylation of acetylferrocene, which gives diacetylferrocene, faster on the unsubstituted ring than the one with the acetyl group? So let's go ahead and understand what the question is talking about. So we got your ferrocene here. First of all, you want to know what the question is asking you. You're treating it with acidic anhydride, phosphoric acid. You get your desired product. So I'm going to draw the desired product here. Now, the question is, you get some side product. The side product places an acetyl group. So I'm going to call this ring 1, ring 2. So the side product places the second acetyl group on the bottom ring. This is what you may get as a side product. This will be a minor amount. What you will not get is this side product. So this is your desired product. What you will not get is your second. I'm not even putting it in a correct position. I'm just saying you will not get the second acetyl group on the same ring. So you will not get dye substitution on the same ring. You get dye substitution on two separate rings. So you have to explain why you get this as a minor product, why this is not formed. That is the question, okay? Now, to answer this, I got to draw the desired product. So I'm going to draw the desired product. That is just having, keep in mind, you can certainly draw this acetyl group on ring number 2. It can be on the top ring or bottom ring. That's just flipped over molecule, okay? Now, we look at the two rings. I want you to tell me which ring is relatively electron rich, 1 or 2. In this structure, this is my desired product. You are going to form this. This is going to be your major product. In this major product, which is the relatively rich electron ring? Which is the ring that's relatively electron rich? That's what I meant. 1 or 2?
1, because it has the side chain with oxygen.
What kind of group is that?
Aldehyde.
No, what I guess, let me rephrase. What kind of group is that? Electron donating or electron withdrawing group?
An electron withdrawing group.
Okay, now you want to change your answer? What do you think that ring 1 is? Electron poor or electron rich?
Could be electron poor because it's going into the side chain.
Yes, and so this is your
Okay.
electron rich ring. So which ring will react? 1 or 2 for the next reaction? So let's say I want to add another acetyl group on ferrocene. Which is the ring that will react? The electron rich ring or the electron poor ring?
Would it be the electron?
So what's going to add, to give you a little help there, what's going to add to ferrocene is the electrophile. So is the electrophile going to be fond of the electron rich ring or the electron poor ring? Electrophile loves electrons, so it's going to go after ring number 2. And that's why you will add your second electrophile to the unsubstituted ring. So your answer will be, you want to label the rings 1 and 2. It'll be easier for you to write the answer. And then say ring 1 is attached to an electron withdrawing group. So ring 1 is relatively electron poor compared to ring 2. The electrophile prefers to attack the electron-rich ring number 2. And therefore, the diacetyl ferrocene, you may want to call this A, is formed and B is not formed. Both of them are diacetyl ferrocenes. Is everybody clear with what I'm saying here? The ring that's electron rich is the one that will continue to react. The ring that is not electron rich, that's electron poor, will not continue to react. It's always the richer ring is going to win out. Okay? I would suggest labeling the rings 1 and 2. I also suggest labeling the diacetyl ferrocenes as A and B. Both of them are diacetylferrocenes. You want to say how ring 2 is relatively electron-rich compared to ring 1, and that's why 2 reacts, and therefore the diacetylferrocene A forms, B is not formed. Okay, it's easier to just give them some labels and draw these structures and explain it. Okay, I'll leave that there. Let me know if you have any questions. Hopefully everybody is coming back to you, the electron withdrawing groups and the electron donating groups. So what is the role of phosphoric acid? Explain with equations and curved arrows. So you want to take a portion of your mechanism to explain this. You don't have to write the entire mechanism. So the role of phosphoric acid is twofold. It is a catalyst, increases the speed of the reaction. Very superficial way to explain the reaction. Second, I'd say it protonates the carbonyl oxygen and makes the carbonyl carbon more electrophilic. I know in the pre-lab I first said nucleophilic. That is wrong. What I meant was electrophilic. Now, you don't have to write too much, except that we will just write a section of the mechanism so that we have the equation and the arrows. So we can write phosphoric acid, not a great Lewis structure. Nevertheless, this will work. Actually, if you want to take it closer to the oxygen, that's good. I'm a little bit further away, but that'll be this. This is arrow 1 and arrow 2. That's all you're going to write in terms of reaction equation. You can use any of those carbonyl groups. It doesn't matter. So the positively charged oxygen will pull the electrons towards it. So carbon is now more fond of electrons, more electrophilic. So that should be enough to answer this question. Okay, that's how it increases the speed of the reaction. But when you look at it mechanistically, protonates the carbonyl oxygen. So that's going to pull the electrons towards it, right? It's just going to pull the electrons towards it. So I would say it withdraws the electron density in that direction. And now that makes the carbon more electrophilic, more fond of electrons. Reaction will occur faster. So go ahead and read quite a few sentences here. We're going to sketch some TLC plates. We're going to do this before the reaction, during, and after the reaction. We did something like this last semester. And then we're going to have all these different things. We're going to have the desired product, acetylferrocene. We're going to have the undesired side product, diacetylferrocene. And if you have any unreacted storing material, ferrocene, we're going to have that. And then we're going to spot it. And once we spot it, we should be able to say which one has the highest RF, lowest RF, and we should be able to explain it. So let's get those TLC plates. We want to have 3 of them. So we're going to have 1 before the reaction, which means time is 0 seconds. Then we're going to have 1 during the reaction. So let's say time The reaction itself is 5 to 15 minutes. So we'll say 2 minutes. 1 after the reaction is done. So I'm going to say time, 15 minutes. So we'll get these. Now we have ferrocene, just to kind of give you the structures again. Or if you already know that, that's good. So this is our ferrocene. Then we have your acetylferrocene. We do need a little bit of idea on the structure in order to determine the polarity, because TLC is very much a polarity issue. Okay, I just wanted one acetyl group, and then we'll have another one where we have 2 acetyl groups. So I'll go fast here. Okay, so which one is the least polar? Let's start with that, least polar. So before the reaction, I'm going to say ferrocene is 1. You're not going to have any acetylferrocene. So I don't know why I had that line there. So before the reaction, if you develop the plate, let's say you will get ferrocene. So I want you to tell me, I want to label these as 1, 2, and 3. This is your diacetylferrocene. So tell me which one. I didn't see anything in the chat. Which one is the least polar? I do need that. Which one is the least polar? I got 1, 2, and 3. It shouldn't be too hard for you guys. Which one is the most polar? You want to take that? You guys there? Everybody's okay? You know what's going on? Yeah, 1 is the least polar. We do need to know that to draw, okay, our TLC plates. This 3 is our most polar because you got 2 carbonyl groups, right? This one is the intermediate polarity. Okay, so I'm going to spot 1, which is ferrocene, and what's going to happen is it's going to travel pretty high up. So this is ferrocene because it's not polar. Anything that's not polar is not going to bind to the plate. It's going to go pretty high up. Now, during the reaction, I'm going to make a spot. Okay, that's my reaction mixture. What's going to happen is it's still going to have some ferrocene because the reaction is still taking place. So you will still have some ferrocene. But then what's going to happen is some of your acetylferrocene is formed, which is actually a little bit more polar. So it's going to be right here. Right, and then your diacetylferrocene is even more polar and it's there. So that's during the reaction. Then I'm going to spot after the reaction. After the reaction, if you had a great day, you should have no ferrocene. Like all the ferrocene is reacted. All you should have is acetylferrocene. Of course, you cannot avoid a little bit of that diacetylferrocene, or maybe it's a great day and you didn't form any diacetylferrocene. So this is how your TLC plates would look. Ferrocene is going to be non-polar. That's the least polar, so it goes way up. Your acetylferrocene is polar, and I'm going to say diacetylferrocene is very polar, so it binds to that silica gel plate very tightly, will not move up. Of course, if you didn't have a great reaction, you might find a little bit of ferrocene even after the reaction. If you had a wonderful day, maybe you didn't even form that green diacetylferrocene. You don't even have to draw that. This is kind of, looking at a general view, assuming all your reactant has reacted, a little bit of side product is formed, majority is your desired product. So it's kind of like an ideal situation here. So what does it mean to reflux a reaction, where and why it's used? So if you simply place the round bottom flask on a hot plate, it's cooking and cooking. You can adjust the temperature, but it's very hard to boil something at a constant temperature. So reflux is a condition where reactants, or you can say where the reaction is carried out at a constant temperature. So instead of hoping the instrument will maintain a constant temperature, what you do is you heat the reaction mixture to the boiling point of the solvent. So if you just heat it to the boiling point of the solvent, then you achieve what is called a reflux condition. So it cannot boil any higher than the boiling point of the solvent. This also can be achieved by heating the reaction mixture in a water bath where the highest temperature achieved will be that of the boiling point of water. So there, what you're doing is the most you can go is 100 degrees Celsius. You can't go any higher. So you just heat it up. It'll eventually reach 100 degrees and your reaction will take place at 100 degrees Celsius. Sometimes you can add a solvent inside the flask like ethanol and it boils. The highest temperature it'll go is 78 degrees. So your reaction occurs at the boiling point of the solvent ethanol, which is 78 degrees. So there are a variety of solvents you can use and you can kind of maintain a constant temperature for the reaction. So reflux is something that we use very often in organic chemistry. So the next question is, why is sodium hydroxide added to the reaction mixture? So during the workup, we do add sodium hydroxide. So let's see why we do that. Now, as I mentioned, you finish the reaction, you have what is called a workup. That's because you have your desired, acetylferrocene. Then you have your acetic anhydride. You have your catalyst. You also have your undesired, diacetylferrocene. Yes, you're adding hexanes and you're, definitely recrystallizing, but you add sodium hydroxide. Now, which of these do you think will react with sodium hydroxide? This is a base. So which one of these will react with sodium hydroxide quite easily? So you got 1, 2, 3, and 4. Which of these 4 compounds will react with sodium hydroxide? Any ideas? That's a base. So which one is the acid? So phosphoric acid is going to react. You're going to write AQ, 3, and 3PO4, AQ, plus 3H2O. So this is one way you can remove one of the side products. Your catalyst will be regenerated. You're going to add sodium hydroxide to take care of that phosphoric acid. So that's one way to remove the phosphoric acid from the reaction mixture. A lot of times that is enough. In some cases, that's not enough. You're asked to add another base, sodium hydrogen carbonate. So if sodium hydroxide doesn't remove all the phosphoric acid, then you will use sodium hydrogen carbonate to remove any residual phosphoric acid. Of course, this is a stronger base. As I said, this should be enough. If it's not enough, you don't keep on adding too much sodium hydroxide because it actually reacts with the ketones. You don't want that. So then you resort to a weaker base. And if there's any trace amounts of phosphoric acid, you can certainly remove that. So here it'll be water, carbon dioxide. I think that should do it. Yeah. It's balanced. So that is with sodium hydrogen carbonate. So I'm going to let you look at this one. What could you have done differently if you wanted more diacetylferrocene? Maybe your goal wasn't to make acetylferrocene. Maybe your goal was to make diacetylferrocene. What are some changes you could have made? Any ideas here? What is it we could have done? You need more acetyl groups. So if you add water, you will kill the reagent, Samantha. You will destroy the acetic anhydride. So don't go that way. I want more acetyl group. So maybe add more acetic anhydride. Just provide enough of that reagent. Don't go the other direction. Don't add water, but instead add more acetic anhydride. Maybe give more reaction time. So these are some modifications that you can do. And if you can come up with any other, you're certainly welcome to add it. One other thing that we do to add more groups is to stir the reaction vigorously. So here you really want to have a large excess of this reactant. So what I've done is I've generated the data for you. So if you open the lab report, you will see it. You can calculate the theoretical and percent yields. So just to kind of review, calculation of theoretical and percent yield is a one-to-one reaction. You want to calculate for for just one acetyl group, not diacetylferrocene. You want to do this for just acetylferrocene. So you're going to go with mass of ferrocene. This is going to be in grams. I've given you the molar masses as well. So here it's going to be molar mass of ferrocene. You should be able to get that from the lab report. This is going to be 1 mole ferrocene. It's a one-to-one reaction. So 1 mole ferrocene on the bottom, 1 mole acetylferrocene on the top. I've also given you the molar mass of acetylferrocene. I think I gave you all of those, so I'll take another look at it before I close today. Molar mass acetylferrocene. So this should give you the theoretical yield. I've also given you the actual yield. It's a generated data, and you should be able to, get the percent yield. So this would be the theoretical yield of acetylferrocene. I'll write TY. So I've given you the actual yield. Actual divided by theoretical times 100 will give you the percent yield. So you should be able to calculate that. The molar masses should be available for you to wrap up the calculation. Our next question is, how can 2,4-DNP tests be used to establish? So this is a visual test on how do you say that you form the product using 2,4-DNP. They should take it back to the previous, I think a couple experiments back on how you did this with 2,4-DNP. So 2,4-dinitrophenylhydrazone and hydrazine is what we are looking at. So I'm giving you the structure of 2,4-DNP. And how do you know that this reaction has taken place? So I'm going to write the product because it's going to give you a visual test that the product has actually formed. The way you do this is you're going to condense. You're going to take these two hydrogens, this oxygen, those go as water. It's a condensation reaction. We have done this, and you have answered this question along with the periodic test. Okay, so which I've just recently graded. So you do know this reaction. And then we have NH, N, and then we're just going to double bond it to C, CH3, and then we're going to continue on with our rest of our structure. So how do I look at this visually? This is going to be a yellow solution. This is going to be a deep red to orange. It can vary, the color varies. Precipitate. Usually they're pretty shiny, they're crystalline. This is called hydrazine, and this is called hydrazone. So the formation of a deep red to orange precipitate indicates the presence of a carbonyl group. You can definitely do this by eye or whatnot, but it's a visual test. Add a couple drops of this 2,4-DNP reagent, which is 2,4-dinitrophenylhydrazine, and then you will form this hydrazone, which is a precipitate that is very shiny. It's got a very deep red to orange color, and that is how you find out that you have, a carbonyl group, ketone. Also gives positive tests for aldehydes, but here you have a ketone. I think this might be the last question. This is an NMR question. It can be proton or carbon-13. You have to use this spectroscopy method to find out how you can distinguish these different, all of them are diacetylferrocene. They're not what we're making in the lab. These are your site products. And you can see how many different types we have and how do we find out, using NMR. So let's start with the structures first and kind of look at them carefully. The first one, which is A, has an unsubstituted ring. So you want to kind of take note of these observations. Okay, it has an unsubstituted ring. And then we'll look at the second one that also has an unsubstituted ring. So that's not going to help us distinguish. That's why I would like to take a note of the differences. So it also has an unsubstituted ring, but it's the bottom ring. It doesn't matter whether it's bottom or top. NMR is not going to distinguish that for us. It's going to show us a ring that has 5 hydrogens, okay, in both cases, both A and B. But what's interesting is these two acetyl groups are next to each other, but these are not. There's one free carbon right in between. Okay, so you want to note that difference. So we're going to see if we can capture that in the NMR. And the next one is C is interesting because you got one acetyl group on each ring. So each ring is going to have 4 free hydrogens. Remember, a cyclopentadienyl ring has 5 hydrogens. In this case, you're going to have 4 hydrogens. So let me move to the other screen here. Having noted the differences, let's see if we can see what we can find out. So let's say we start with the proton NMR first. So we have 5 free hydrogens, 5 free hydrogens. So that's not going to help us distinguish. But here you'll have 4 hydrogens. So when I'm talking about hydrogens, I'm talking about the hydrogens on the ring. I'm not counting the methyl group. The methyl group is everywhere. Okay. This is going to be 4 hydrogens on the ring. These are aromatic, so I expect them to come between 6.5 and 8, but the integration would be for 5 hydrogens for the first structure, 5 hydrogens for the B, but then it'll be 4 and 4 for these. These will be 5 and 3, and this will also be 5 and 3 hydrogens. So the integration is going to be our first difference. Integration is going to distinguish C from both A and B. However, it does not distinguish A and B, okay? So keep that in mind. Now we'll go to distinguishing between A and B. Right here is a free hydrogen. And then we got 2 hydrogens here. This hydrogen will appear as a singlet. Here, you're going to have 3 hydrogens. This will be a doublet. This will be a doublet, whereas this will be a triplet. this will be a doublet, and this will be a doublet. So for A, it'll be 2 doublets, 1 triplet. And for B, what's interesting is 2 doublets, but 1 singlet. That's the key thing. That's what is going to distinguish A and B. So this is how the proton NMR will distinguish these 3 isomers. If you like, you can move on to the carbon 13 as well. But I don't think it's necessary because the proton NMR will pretty much resolve it for us. So integration is important. It's going to be a ratio of 5 to 3, 3 to 5. That is not a big difference. The top ring is 5, here the bottom ring is 5. So the ratio is the same. It's not going to help us distinguish A and B. But here it's 4 to 4, which is 1 to 1. Okay, so that is going to help us distinguish C from AB. Now it's the splitting, it's the multiplicity pattern, which is going to help us distinguish A and B. So take a look. Let me know if you have any questions here. I hope everything is making sense. You guys are like awfully quiet. I'm sure it's overwhelming after a couple of weeks of break. But I would suggest that you start working on this course right away and try not to push everything to Sunday. That's what makes me nervous. By not making anything due this week, but making everything due next week, I'm really hoping that you will come up with a study pattern to distribute the work evenly between this week and next week, okay? So I'm going to stop the recording here, and that's all I have for this lab. And then I'm going to open up the next lab pretty soon, today or tomorrow morning. So those who like to work ahead can start working ahead. But other than that, that's all I have for you today, okay? Let me know if you have any questions. I'll stop the recording and start sharing.